All right, let's get started. With a class this size, it's going to be hard, so keep track of everybody's name, but at the very least, I got to do a attendance, mainly because I need to make sure everybody is in Main Street. So I'll read your name, just say here, present. If you don't hear your name, let me know, because I have to add you manually to Main Street, which is not a huge deal, but it does need to be done. And then the other thing is, or at least add you to Brightspace, you do need to check because it should automatically populate from Main Street. So if you're registered in Main Street in either 427 or 422, you should automatically get enrolled in this class. Okay. So if something happens, I don't know exactly what, but we'll be using Brightspace a lot for classroom management. I suspect most of you all are very familiar with Brightspace at this point. So we'll go through a couple things. I use it pretty extensively because it keeps me honest and it makes classroom easier to manage. All right, so let's start. Ryan Abedi. Drew Adams.
Here.
James Bertolino.
Here.
Casey Boucher. Hey. Cole Brown. Thought I saw him. Nicholas Casanova.
Here.
Aiden Davis. Clyde Day.
Here.
Connor Devine.
Yep.
You are again. Divine.
Yep.
Jason Durasher. Andrew Farrington.
Yeah.
There was somebody who graduated from this program about 15 years ago with exactly your same name. So at the engineering job fair, there's a company called SGC.
Yep.
I highly encourage you to go see this because there is an Andrew Farrington that works there. He has a lot less hair than me. But anyway, that might be a good leg up on anybody.
Yeah.
Kane.
Yep.
Joe Fitzgerald. Mason. Nate. Kendro. Let's see him. Alan's here. Yep. Luke. Oh, there you are. Luke Herrick. Yeah, that's not Luke Herrick. Okay. Keith Holland. Michael
Here.
Kuzbin.
No. It's Jacobeeson.
Jacobeeson. Okay, I got that completely wrong. Thank you. Kate Johnson. Wyatt. Yep. Rita. Let's see her. Malachi Lowry. Michael Marr.
Yep.
Taylor Martin. Jonathan Maxwell. Lee. Benjamin Mock. Gombe Mwabi. Andrew Monroe. Yep. Garrett Noble. Zoe North. That's page 1. We still have a little more to go. Derek Holas. Caden Pattershall. Adam Rex. Niall Regas. Landon Robitaille. Paul Rudman. Luke Saucier. There's this of Luke. Jaden Spalding. Yep. Austin Speed. Leo's here. Noah, I think, is here. Yeah. Riley.
Here.
No, not here. Riley Tebow. Aaron White.
Wait.
Oh, Riley's online. Okay, that's right. Aaron White, you raise your hand. Yeah, okay. And Cully, didn't see him. All right, that's 46. So anybody's name I did not announce. Okay. Thank you for that long list. Pretty atypical for a 400 level class, but we'll make it work somehow. So yeah, I think this is one of my biggest live classes I've done in a long time. So there'll be some adjusting, but that's good. I like seeing a lot of faces. So please come to the live class. It'll be a lot more fun for me and hopefully a lot more interesting and fun for you. I actually have a fair amount of real world experience in this industry. As I was telling my earlier class today, I do still a lot of active consulting in this industry. That's one of the differences probably between EC and EET. The research that we do is more applied research, trying to figure out how to solve problems that are currently happening, where the ECE focuses more on research for future developments and applications. So a couple projects that I've worked on, just to give you some credence, I know what I'm talking about. I worked on about a $500 million project in Long Island. They're going to upgrade in lower Long Island, getting into basically New York City. They're looking to upgrade their utility incoming lines. Anybody have a rough idea what the voltage is you typically see for like high voltage transmission into New York City? What is it? 545? Close. It's 345. So in New England, the highest voltage level that we have that's AC is 345 kV. Anybody know what the highest voltage is for DC? There's two DC lines in New England now, right? They just energized the New England Clean Energy Connect, which is the one that comes in from Hydro-Quebec and goes through Maine and terminates in the Lewiston Auburn area. There was a lot of discussion about that. A lot of people sued and some still got built anyway. I actually just we went to Montreal this summer for a soccer tournament and we actually drove under the line. And anybody know how you can tell the difference between a DC line and an AC transmission line? There's one really obvious thing.
They're not left wire.
Yeah. AC has 3 wires per, well, it has 3 phases. It can have multiple wires per phase. How much does DC have? 2, right? There's a plus and a minus. So the line that goes into, that's called Sandy Pond, which is near Ayers, Massachusetts, or Devon, Massachusetts. I found that out because we went to another soccer tournament this weekend in Devon's. That's DC line goes in there and it's plus minus 450 kV. So the voltage potential difference is not 450, it's 900 kV. That's the highest voltage class, I think, in all of the United States. They have 765 kV, but this is 900 kV if you go across the 2 poles. That's the largest, and it's just 2 wires. You have a plus and a minus. And technically, you don't even need 2 wires. In DC, you could run 1. Where would be the other wire? You're sitting or standing on it. Ground, yeah. You can use ground in Canada for a return path. You can't use that in the US. It's against the FERC mandates or whatever like that. So if you get to Canada, you might actually only see 1 line. Right now, there's 2 that go all the way into Canada. Anybody know why we run DC? Why is a new line coming in from Canada, DC, and not AC? There are some major advantages to DC, but there's some disadvantages too, right? Cost. DC is far more expensive because you got to convert all that AC to DC and then back again. So you have these very expensive AC to DC and DC to AC converters. And it's not like, you know, your power supply here that you can buy for $20. I mean, you're talking the one that goes into Ayers, Mass, it's capable of doing about 2,500 megawatts, which I'm pretty sure that would not be able to produce. So very expensive converters, but you only need 2 wires, not 3, so you can have less spacing. But generally speaking, it's more expensive to run DC than AC unless you have really long lines. So why do you think they ran DC? I doubt. Yes. It's a good guess, but Canada is 60 hertz. All of North America is 60 hertz. In Europe, they run 50 hertz. In Japan, they have a mix of 50 and 60, so they can create some challenges. But technically, you could not interconnect 50 and 60 hertz. But the reason why Canada does everybody know the term synchronously or versus asynchronously? Hydro-Quebec, what's that?
Yes, I'm kicking my head.
Hydro-Quebec does not want to have to run synchronously with the US. So if they ran a 60 hertz line, their frequency and voltages would be pretty well locked with the US. But because they run DC, they can have a different frequency. They can be, and they're still 60 hertz, but they can be anywhere they want to be on the sine wave, and we can be completely independent. Where for here, we have to be at the same point on this AC sine wave that is New York, because we all interconnect. So it makes it much more challenging. So they would prefer to go asynchronously. So most of the lines that connect in major transmission lines that connect into Hydro-Quebec is a DC line, at least going to the US. They do have some AC lines that connect into New Brunswick, but that's kind of the reason why. So I worked on a project. The reason why I'm saying this is it's 900 kV. It's higher than what you see in New York City, which is 345. But interestingly enough, you don't actually see high voltage transmission lines in New York City, do you? Anybody want to guess as to why? Yeah. Where would you put the wires if the buildings are 50 stories above ground? You do, they do exist. They're just underground. Anybody know what type of cables those are?
Big one?
They're big cables for sure, yes. But they're called pipe type cables. What it is there's a conductor that is copper or aluminum, and it's actually located inside of a piece of pipe, and then it's got spacers, it's got insulators all around it. And then what they use is they use oil as the insulating medium. So they pump oil from point A to point B. They call pumping stations, and that's how they help keep the cables cool. And then they can run them at higher power levels. That is going away a little bit because you can buy solid dielectric cable, which just basically means the dielectric is just a piece of plastic essentially. And you can run 345, 760, you can just run as high as you want. It just becomes more efficient for, at least when you look at the I squared R losses in the line, when you run pipe type cable. But pipe type cable, you get leaks, the oil leaks, you got to clean it up. You can get some real problems. And so you don't see as much pipe type cable anymore. So I worked on a project. It was going to replace one substation. So that's some new phase shifting transformers can interconnect. And just the modifications to tie into the existing PSEG, that's actually LIPA, Long Island Power Authority. Just to do that, it was going to be $500 million for one substation. They were talking for this one particular project to upgrade some of their 345 was going to be close to $4 billion, which is 4 times bigger than running the New England Clean Energy Connect. I also worked on another project in Long Island. This is out in Southampton, and I talked about this earlier. Southampton is the ritzy part of Long Island. So you can't just put a substation up there. Those are ugly, right? Steel and insulators and breakers. They don't look real pretty, not when you've got a $50 million home next to it. So all that stuff has to be put in what's called GIS or gas insulated switchgear. And why gas insulated? Because you use gas, which has a much higher insulating characteristic than air. So you can make it much smaller, which means you can put it inside of a building. So you can actually conceal or hide the fact that there's a 69 kV transmission line. Outrageously expensive. 69 kV is a pretty low voltage for GIS, but they're willing to spend $200 million. Well, they had to spend $200 million to put in a 40 megawatt battery storage facility because the residents of Southampton have these really ridiculous ordinances that prevent you from building anything that looks remotely industrial in their beautiful land. So a couple projects that I've worked on, I've done extensive experience in this. And so hopefully I'll be able to bring you a lot of practical real world examples. And maybe we'll bring in a guest speaker if we have somebody who has a particular area of interest. The other thing too is, and I know this is probably a little more for ECE students because the EET students already know this, there are tremendous demand for jobs in the utility power industry, particularly in Maine. You wouldn't think Maine as being like a juggernaut, if you will, for the power utility industry, but there are probably half a dozen companies that are in Maine that hire hundreds, if not thousands of engineers to do projects. Like I was talking to one of the previous classes, and they had interned at Power Engineers, which is located in Hollowell, Maine, which is a one-horse town just outside of Augusta. And they probably have 70 engineers working in an old, I don't know if it's a theater building or something like that. And they're designing projects for things in Galveston, Texas, Florida, all over the US, because we do really good work here. And what you're designing here in Hollowell, Maine, it still works in any part of the country, any part of the world, actually. So tremendous demand. And what you're starting to see, and we'll talk about that a lot more here, is just the growth. So everybody wants this latest smartphone, everybody wants the latest technology, The problem with that is that stuff is throwaway technology. So anybody here have a cell phone that's more than 4 years old? 4 or 5 people, really? Wow. You're still getting OS updates? So you don't have one. You are off the list, right? That's okay. I like to keep my stuff longer, but people upgrade. I mean, the phone companies encourage you, right? Because you get a trade-in for free, and then you can switch companies and you can get the brand new iPhone, whatever, because it looks really cool. But the utility system can't be that way. You can't just throw it away and replace it. It takes billions of dollars to build these projects. And if your cell phone doesn't connect to, whatever service you have, what do? You get frustrated, but you're like, well, I'll go back to it in an hour and see if it's available again. What if you go to the bathroom and you flip your light switch on and the lights don't come on? What do? You start troubleshooting immediately. Oh, I got to replace the bulb. That didn't work. I got to go check the breaker. That didn't work. Now I can start getting nervous. What's going on? The weather's good. Why don't I have lights in my bedroom? Why are the lights off in my apartment? You start to be like, whoa, this has to get changed really quickly. And so the reason why I'm pointing that out is in the utility industry, it doesn't have the sex appeal, if you will, if you want to, for lack of a better term, that smartphones have and all the technology stuff. But in some ways, it's way more important because you could live your life, not for a long time, I imagine, but for a short while without your cell phone. How long could you go without electricity? I mean, some of us have gone for days, right? Because we've lost power. But even then, it's like, well, let's go buy a generator, right? You can go to Home Depot and buy 3,500 watt generator for $300 and then provide service to your house, some basic service. So we can't have a grid that's not reliable. So these things have to be built with such high standards and maintained and operated at such a high level because we need reliability. And if you don't build it, our friends in the federal government who hand off authority to NERC and all these different regulators are authorized by the government to issue fines. And this has happened in the Public Utilities Commission for Maine. This was about 3 years ago, but Central Maine Power, Avangrid, depending on who you ask, I'm trying to think, they used to have another name, with a V, but I can't remember now. But they actually applied for a rate increase, and the PUC said, no, you're not competent to get the rate increase that you want. And so as a result, they were rejected, and then they had to go back to the drawing board and figure out how to reduce costs to be able to provide that. I worked on a project a while ago this is like 10 years ago, that Florida Power and Light, they had some technicians that did some major screw ups and they kept screwing it up. And so they got issued a $2 million fine. Who are you going to complain to? There's no judge, jury next to you. You're just paying the fine. There's no choice about it. So when you're talking businesses, it's very different. So we're going to talk a lot about the processes to analyze, design, build power systems to give you a small taste of what it takes. And then depending on what you want to do, you can go from there. If anybody here is a junior, not graduating, ISO New England has a wonderful, and we'll learn more about internships from other folks, especially as we get closer and closer to the job fair. But I know that the internship program at ISO New England is really good. They actually rotate you through a bunch of different departments and they send you on different site tours. So you really get a very broad smattering of what to do. I think they do a really great job. I don't know if they have any internships posted as of yet. It's kind of early to do that. Yeah, these are just the intern stories. I don't think that they're posted as of, well, let's see. Yeah, they would normally be posted here. But one of the things they want you to do is they want you to have power as a background. So concentration in power systems or pursuing one is one of the things they want you to do. And taking this class is one of the keys to getting the concentration. One last thing, if you look at this map, do you notice anything interesting about it? It's kind of hard to tell. Do you notice anything interesting about this map? Whoops. Some parts of New England aren't green, which means some parts of New England aren't part of New England, at least from ISO's perspective. So Vermont and New Hampshire, those are all part of New England, but Northern Maine, Presque Isle, is technically not considered part of New England. So if you were to call up ISO in New England and say, hey, Presque Isle's having a problem, they're like, that's not our problem. That's not part of New England. from their perspective. And you can see that from the ISO New England transmission map. And this is readily accessible information. And this is free, you can access this. So let's see, I think it's the system. Nope, not that one. Where is it? Is it this one? Here. So sorry, it's not really super legible, but you can see up in Presque Isle over here, the top right, it doesn't connect to the rest of New England. So this part of Maine is not considered part of New England. And there actually is an independent system operator for Northern Maine. It's called Northern Maine ISO. And it's actually located, I believe, in the Burson building in Hamden, Maine. And it's located in Hamden, Maine at the Burson building because it has additional security. So you can't just walk in and say, hey, I want to look at the transmission map. Have a nice day. Let me walk around. These all have to be secured. You have to have, kind of limited access to get to those places. We can get tours of those. So if anybody's interested, we could possibly set up a tour. It's just not as easy as being able to walk in, but they actually have buses and voltages and all that stuff primarily for Northern Maine. If you were to go to Augusta, they actually have a detailed map for Maine because they have a lot of the CMP territory. Yes, sir.
I got to work at their, they only showed us that one.
Yeah.
Yeah, that's good.
Yeah. So one of the students here was saying that they interned at Versant this summer and they got to look. Did you even get to go into the room or?
No, there's like, you can turn card.
Yeah. So that area is restricted for even interns can't get in there, and you have to have a special access to get in there because if you know what you're doing, don't know what you're doing in some cases, you could really lock up ISO New England, Northern New England for a long period of time. So, and then if people lose power, people can die. It doesn't take long before a loss of power. Like if you're on a well and you have no well water, you don't have water to drink. If you have some health issues and you have special equipment to help you live, losing power for a short period of time can really be the difference between life and death. And a lot of that is improving now because we have battery storage systems. Like I fervently believe that when you go to Home Depot and you buy a little portable generator, those are going to be replaced by more modular batteries. So you charge up the battery and then you might be able to get 5, 6, 7 hours at maybe 1 kilowatt of load. You don't have to change the fuel. You don't have to maintain it. It makes things quite a bit easier. But the other thing that's really good about ISO, and this is something that hopefully is really interesting to you, is it will tell you real-time energy prices here. In the green usually means good. These are incredibly low energy prices. Very, very, very low. When you're talking $25, that means that's $25 per megawatt hour, which equates to 0.025 cents per kilowatt hour. So very, very economical time to buy power. And you can see, look at the load. The load in New England is 10,190. Very, very low load. This summer, does everybody remember, was it June 27th or something like that? When it was like unbearably hot, 97 degrees. Anybody want to guess as to what the price of a megawatt hour was? It was over 1,000. I actually took, let me see if I still have that up. I took a screenshot of that because I guess I am that nerdy. That, where is it? I'll just open it up. It should be on the desktop here. Let's see. Maybe it's not there. Maybe I put it in the folder. Let's see. I can't find it, but I did take a picture. I might have it on a slide, but it was over $1,000 a megawatt hour, which translates to over $1 per kilowatt hour. And what do you pay on your electric bill? This is energy plus distribution. So it's supply and distribution. You pay about what, 26, 27 cents? That is the supply, which means what the generators are charging, because in New England, we're a deregulated market, which means the generation isn't allowed to be owned by the utilities. So they have to pay for the energy, and then they actually own the transmission and distribution, and they have costs associated with that. So the combined cost of those 26, maybe 28 cents a kilowatt hour, but the energy cost alone on that day was over $1 a megawatt hour. So who was losing money? Not the utilities, because they'll just go back to the PUC and say, hey, we paid way more money than we were allowed to sell, so they're going to just bump up rates. So when things happen like that, that's usually a really bad case. One other thing too, this is interesting. Why is the load at 8 o'clock 12,000 megawatts, but then at 12 o'clock when everybody's at work and awake and at school or whatever, why is it like 10,000 megawatts? Why is it 20% less than what it was at 8? But they're all at work, working hard on their computers. What's that?
But they're all involved, right? But like, burning up thoughts.
Well, sort of, but generally speaking, when people are at work, right, they're making widgets and they're doing some production because they're at their jobs. I mean, if it's a white collar job where you're just working on a computer, it's one thing, but if you're literally making stuff, right, there's a lot of electrical demand. So electrical demand tends to be higher during the day than at night. But this is the opposite of that. What does that mean? Somebody took some bad data? What are you all forgetting? What's that? Say that again? Not batteries. Anybody have a pair of sunglasses I can borrow for a moment for added visual effect? Yours, here. Pass them forward. Other than to look cool, like Alan, why would I put sunglasses? Say that again? Solar. So at 12 o'clock, at 12 o'clock, it's bright and sunny out. All that PV in New England is cranking to the point where it's more than 2,000 megawatts just in New England alone. So the load starts to get up, then people start getting home. Why does it spike so much? That's 8 o'clock. Why is it spiking at 8 o'clock?
No sun.
Sun's down, right? It's dark. So all that PV that is on people's homes, it's not doing anything. And so this is a real challenge to the grid because now you have variable supply. Is it sunny or not? And the load is variable. Let's see if I can annoy everybody. What am I doing other than annoying you when I do this? Changing the load. So if everybody's changing the load and nobody has any real idea about how that's happening, you don't even know what the load is. They're predicting a load here of 10,010, but the load is 10,246. So you're not exactly sure of the generation because it might be sunny in Boston, but it might be cloudy in Bangor. Just depends on what's happening in the sky. And you don't even know what the load is. So solving this problem is very, very difficult. And that's part of the thing that we're going to do, which is come up with some ways of, hey, how do we make all of this stuff work together? Because this is not new technology. The power system has been around for over 100 years, right? Anybody know where it started? Where was the first electrical distribution system in the world? It might be an obvious, it might be not an obvious. Chicago World Fair? No, that was electric arc lighting, close. New York City. Thomas Edison, remember? Thomas Edison did DC, and he had DC dynamos that he was running with whatever fossil fuel, coal, whatever, next to some place in Manhattan, which had, multi-story buildings then. And so they had to run elevators, they had to run lights, and you couldn't run gas, it wasn't safe. And so they started with really super populated areas. And so you found a lot of demand, in big cities. It wasn't until much, much later on when they started moving out into less populated areas when you actually had a demand for that. Anybody know the original company that Edison founded? The original company was Edison Electric. Then it became General Electric. But in the 30s and 40s, the terms general and standard were four-letter words. Nobody liked those terms. So what is General Electric called now? Well, that's a specific one. It's just GE. If you looked high and large on their GE website, you might see where it says General Electric, but they just shortened it to GE. Anybody know who Standard Electric is? I mean, Standard, it's Standard Oil.
Aren't they modeling?
I thought it was Mobil. Could be Chevron. I thought Chevron was a Venezuelan-based company.
Shell was Venezuela-based company.
What's that?
Shell.
Shell is a Venezuela-based company? Well, let's take a look.
It's ExxonMobil.
What's that?
It's ExxonMobil, isn't it?
I thought it was ExxonMobil, but yeah, it says ExxonMobil. Why'd they get rid of Standard? That's just because people thought these big terms where they had monopolies were a bad term. So now they just changed the name, just like GE did. So not the greatest information, but we'll talk a little bit about that. So getting back to the syllabus, this has hopefully everything you'll need for the semester. Even some events, we'll talk about homeworks and stuff like that. It'll be all managed through here. It's getting impossible to do things just with paper. So we just upload your homeworks. If you do tests in person, then those will be done, with paper, but you can do exams online. We'll talk about that as we get a little bit closer. I also have the Zoom links for both the lab as well as the class. The lab is going to be simulation. And if you look through, I actually have some pre-lab stuff that I've recorded already. And you're welcome to take a look at those. If you want to go through the labs in advance and try those out, you can do that. Or you can wait until we do the live lab. It's totally up to you. I just do that as another way to give you more information if you want to do it or not. We'll still have live lab, but we'll go through it. But if you want to do the pre-recorded videos, you're welcome to do that. The syllabus is here, and your whole semester is already laid out.
Oh, thank you.
What's that?
I saw the class of the whole semester.
Yeah, we got it all laid out. Dates and content that we'll cover. Again, this is tentative. Why is it tentative? Because if a class gets canceled for one reason or another, we have to move things around a little bit. But you know all your exam dates, etc. The only thing I don't have in here is the final exam. That's set by student records. I don't have any control over that. I could add that to here, but I think it's fine. That's the way we do it. Okay. So again, you can take a look at that. And then inside the classes, like today is 9-2, in here will be the presentation that we'll try to cover that day. It will also have, once I'm done with this class, because I'm recording it, because there are a bunch of people who are taking this class asynchronously. So I record the class, it'll be available to them, and the link will be here. It just takes a few hours for it to be processed through Zoom and YouTube. That class link will be available to video, but that's an opportunity. If you want to rewatch a class, feel free to do it. Like when I was in grad school taking classes, I would rewatch videos all the time. Just to say, I didn't quite get that content, so I'd rewatch the video, and I could watch it at 1.5 times speed or whatever, and be able to get a little more understanding of the material, but do it with 45 minutes as opposed to a full hour and 15 minutes. So it's a way. Hopefully, you'll get good information, and then you can enhance your learning and whatnot. Okay. I also like to use MATLAB a lot. How many people here are familiar or have used MATLAB? Fair amount of you. Okay. If you haven't, that's okay. I did this in my previous class. MATLAB is a calculator for me. It's just a powerful calculator. And so I try to write MATLAB scripts in this class in particular, because solving through some of the problems can be really challenging. But if you can see a step-by-step process in MATLAB, there's no guesswork. You can just see exactly what needs to be done. So if we do some work in MATLAB during that class, I'll go ahead and post the .m file, which is just a script file that if you have MATLAB, you can run it from the MATLAB program. MATLAB's a free download. if you're a UMaine student, just go to umaine.edu/IT, download the software, make sure you log in or set up an account with your Main Street ID, and you should be good to go. It's about between a 4 and a 5 gig download. So I made a joke earlier this morning that probably went over not too well, but I said, don't do it on dial-up. Anybody here know what dial-up is? Do?
What the?
Dial-up? Okay, you don't know because it's gone, but it's used to use a phone line. You had to call in and you were down limited to 128K was the speeds, I think. And AOL, they were a huge company back in the 90s. I think they just closed their dial-up lines. I don't think you can get dial-up there anymore. You probably still can in certain places, but everybody now just has either cable or fiber or something like that. Like UMaine on campus, we have what, 1 gig speeds? So it's very slow. So don't do it on a dial-up line if you can access one of those. Okay, I think that's all I wanted to go. The syllabus, if you have more questions, feel free to ask on the syllabus. Any general questions from me? Yes, sir.
You said the labs are gonna be simulated, so are we gonna do that year lab, we said we're doing live labs?
We'll do the live labs, right? So you'll be given a problem, and what we'll do with the labs is I'll help you through the process. So we'll mainly do them in MATLAB. So we'll do it's basically the lab in this class because we can't really work on power systems analysis because you can't realistically test a 345 kV system or even a 15 kV system safely unless you get extensive training. Most of the time, if you do testing on a system, you try to de-energize it to work on it. It's pretty rare that people actually do real testing on a 15 kV system, anything medium voltage, which is usually about 1,000 volts or greater. It's just not safe unless you have a lot of training. So it's hard to do that. So we just try to do the stuff in a simulation environment. Okay. But yeah, we'll just do simulations in MATLAB or whatever. Other questions? Okay. Let's go over. I have a short presentation. It's 23 slides, but it should go fairly quickly. So 427, we're going to do power system modeling. We call it power flow or load flow as a technique we'll do. And more importantly, effects on voltages. And voltage impacts are a big deal. So we'll have to analyze that. Fault analysis is number 1, because you can't have a real world system that experiences a fault and is unable to isolate that fault. If you do that, people could die, equipment can get damaged, and it could drag down the rest of the system. In 2003, there was a major outage that affected 26 states, all because a line in Ohio touched a tree, or the tree touched it, depending on your perspective, and took out 26 states. That's really, really, really bad. There was a lot of work that was developed for that, and it was because of some bad assumptions and some relay settings that caused that. Our fault analysis will include non or asymmetrical faults. What's the most common type of fault in the world? Line to ground, single line to ground fault. If I stick my finger in the socket and I go to the right or the wrong terminal, depending on your perspective, that's a single line to ground fault. We'll look at those non-symmetrical faults because everything, if you've done any AC circuit analysis to this point, you've pretty much assumed a balanced fault, like both phases get taken out. But the most common one is a single line to ground fault. The other 2 phases don't experience a fault. So that makes the analysis very, very difficult to do for us. So we'll introduce what's called symmetrical components to cover that. And then we'll look at some basic fault detection methods. You probably know the most common one, which is an overcurrent device. Your house has all kinds of them, right? You have breakers. Hopefully here, nobody has fuses in their house. Maybe you do, but hopefully not. So breakers, those just work on overcurrent, very simple, but those are very dumb. They don't do much for you, and they don't allow you to really get into a more specific fault analysis. So we'll look at that. And then we'll look at some small or large systems, because that's what makes power system analysis difficult, is it's not the fact that it's really difficult material. It's all AC circuit analysis that you all are experts at probably by now, but it's because a system have 10,000 buses. So you have to analyze systems with 10,000 buses, which makes management of the data very difficult. And so that's where power systems analysis gets more complicated. This is what you should know. If you don't run for the door screaming. But we'll get you up to speed if you haven't got it. Phasors and phasor diagrams, because in this class, that's what we deal with, steady state phasors. Power triangles. I use the term real and reactive power. Some people say real and imaginary power. It's not imaginary power. It is real power. It's just not doing any useful work. And then the apparent or the total power. If you don't know three-phase, we'll cover that a little bit again, but because the utility system is a three-phase system, we have to understand three-phase and we have to understand phase and line quantities. We've got to get at synchronous and induction machines, more synchronous machines, because even though we have a lot of renewable energy, which a lot of that stuff is inverter-based, like solar is all inverter-based, right? Solar, what is the output of a solar array? Is it AC or DC? DC, but we interconnect into an AC world, right? So the most effective and cheapest way to do that is to use a static inverter. Very simple. But in the real world, most of the time, like 80% of the power in the US comes from fossil fuels or some sort of system like that. That would be done with a synchronous generator. Even renewable energy, a hydroelectric dam, that's determined by a synchronous generator. It converts mechanical energy to electrical energy via magnetic field. So because so much of that power is from synchronous machines and will be for the near or foreseeable future, we'll cover synchronous machines. Induction machine is just a thimble amount because most of the time induction machines don't really impact us too much other than voltage drops. Because you're dealing with a 10,000 bus system, at least, you really need to have linear algebra. You need to be able to partition things in matrices to make it understanding. So I don't expect you to be an expert of it, but at the very least be able to put things into matrices to make it work. And then MATLAB, we already talked about that. We've kind of talked about this already. So great work. Like I said, the Andrew Farrington example, right? He's at SGC. Tons and tons of job opportunities still. AI will not be replacing power systems engineers. Not for maybe forever, who knows? First off, there's not enough learning, right? Because that's how AI works. It has to do enough learning. So it practices until eventually, or learns until it has a model that it can come up with answers really, really clever. But it's only as good as the data that you're feeding it to help it learn. Well, the stuff that we do, there's not a lot of material out there to help it learn. Yeah, there's books, but a lot of that stuff has very specific applications. And so you don't have the same learning models. Not like in healthcare. In healthcare, there's so much research going on in healthcare that they've even talked about some doctors potentially being replaced by AI models. Like if you take a bunch of lab tests and some symptoms of the patient, you feed it into an AI doctor and they can diagnose with pretty good accuracy what your symptoms are. They haven't actually, proven that yet, but there is a lot of research going on. We're still one of the few universities that does power because it's not sexy. It's all it is. Everybody wants to design the next smartphone. Not everybody wants to work on equipment that looks like it's 100 years old. Smarter grid. We're getting smarter and smarter. So is in our grid. Our grid has to be able to respond to faults in a better, more effective way because we want to limit the impact to our customers. Right? And who rules the grid? It's the customer. Why? They pay the bill. If you're dissatisfied with your power company, you're going to disconnect. You'll do something else, right? And so the Versants of the world, you may think, oh, they're mean, bad utilities. They actually care very much about the customers because that's how they make their money. If all the customers leave because their customer service or quality of their supply is so bad, they won't exist as a business. So what dictates everything is the customers. Where is the load going to be because I can pay? So that doesn't mean, you can just build a load site, out in the middle of nowhere. You still got to pay for the transmission to get there. But if you want to build a new Walmart, Versant will figure out how to get the power to you, as long as it's within a reasonable distance and accessible. Okay. Anybody know how much a typical Walmart, like a supercenter, would be in Bangor? How much load they typically would put? Like what size transformer would it be? Anybody want to guess?
13.5.
That's the voltage that's supplied. So that could be the voltage. What would be the actual size of the transformer that's feeding the Walmart? Because you're not running 13.5 into Walmart. That's too much liability. Everything going into Walmart is 480 or less. So what would be a typical transformer to step that 13.5 down to 480? Yes, sir.
500 MVA.
500 MVA. Multiply by 10. 5 megawatts. Those are 5 MVA transformers for those supercenter. And it's surprising because lighting is not a big heavy load. What's the biggest load on grocery store? Refrigeration, heating and ventilation, right? Huge, huge, huge. Not as big as like, and I always use the example in my other class, not as big as a restaurant. Why would a restaurant have such high load? Ovens might be gas, right? Yeah, but usually microwaves don't cook a lot of food. I mean, they might warm things up. Keeping the food cold, so you have some refrigeration. You also have a tremendous amount of ventilation because if you're enjoying your dinner and then all of a sudden you smell some burnt French fries, that dinner might not taste so good anymore, right? Because the ventilation's not working. But what tends to be the biggest electrical load in a restaurant? To me, it always surprises me, but it is. It's the dishwasher. Think about that. When you're at home, who here has a dishwasher in their apartment or their house? How long does it take to clean the dishes?
An hour.
An hour? Do you think they could wait an hour for a clean set of dishes at a restaurant? Maybe a minute, maybe 2. So the dishwashers have to run at incredibly high temperatures and pressures to sanitize the dishes. So their water temperature, 160, 180, because you sanitize everything like that, right, at those kind of temperatures. And also with such high temperatures, stuck food or whatever gets cleaned off very quickly. Because you can't wait an hour for a set of clean plates to come out.
Yeah.
So really, really high temperatures, big heaters, big motors and pumps to go ahead and pump the water pressures up to really high values, just dishwashers. And those are like really expensive. Those Hobart commercial ones are like $8,000 because they run at such high temperature. And all that stuff is regulated because that's sanitation, right? You've got to sanitize the dishes. And if anybody here ever worked in a restaurant,
Yeah,
the dining commons,
Yeah.
do you ever pull the dishes out right after they come out?
It's hot.
It's burning because it's 160 degrees. It'll burn your skin.
Goes faster. 5
goes-
minutes, all the dish is done.
5 minutes, and that's a crappy one. I bet you if you go to a fancy restaurant, it's
Yeah.
2 minutes.
That is old. They've
Yeah.
been thinking about it, letting it, but they can't do it. It's too expensive.
Yeah,
Like,
they move a lot of product there, but again, the idea is you got to sanitize things so it's burning hot. It's, I think the minimum temperature they run at like 160 degrees because sanitation happens in 1 minute with 160. Anybody know about the process of pasteurization? We all drink milk, or most of us drink milk, right? At least in your cereal. Why? How do you pasteurize milk? You heat it up to 120 for about 10 minutes and it kills all the bacteria. If you heat it up to 160, it's less than a minute to kill all the bacteria. The downside is the milk doesn't taste so good at 160 degrees. At 10 degrees, at 120, you can do it for a longer period of time. And I guess it doesn't change the flavor of the milk enough that most people will notice it. But you run at a higher, you run everything at 300 degrees, right? It pressurizes, it sanitizes like that, and then everything boils off and it's no good anymore. So yeah, that's the reason why. So let's analyze a map of a power system. This shows different types of generation as well as transmission dotting the eastern part of the United States. And you may laugh and say, no way, this isn't real. How could something, let's say here in Connecticut, where this yellow line is, how can something affect us all the way up in Bangor? Which is kind of hard to see, but I can tell just by these transmission lines, Bangor's right about here. How can something down here in Connecticut get a long way to go? Well, maybe 8 years ago, there are 2 nuclear power plants. You can tell on the yellow color that says uranium, which in other words is nuclear. 2 nuclear operating plants running full out. So about 2,100 megawatts instantaneously tripped offline. And that almost tripped people in DC. they said they had such wild frequency excursions with the casino. It was Sunday morning, so lightly loaded, but this was putting on a lot of megawatts relative to the load. And we almost lost people in Bangalore. They said they saw major frequency deviations all the way down to Florida, 1,500 miles away. Which makes this a good and a bad scenario, right? It's great because things move fast, right? Electricity moves at the speed of light. Electricity is by far the greatest transmission medium there is. You have energy that moves at the speed of light. Our friends in mechanical engineering can't hold a candle to us. There's nothing anywhere close to being that efficient and that effective at moving energy. You have thermal in mechanical systems and physical, right? Like actually physically moving something. That's it. That's why you don't see big thermal plants. You know, like campus is a thermal island where we have the steam plant provides heat to the buildings, but you don't see that all the way into Bangor. It just wouldn't be effective or efficient. But electricity goes all the way up from Orrington, which is beyond Bangor, and there's a sub transmission line that comes right at the top of campus. That's a piece of cake. So all that is interconnected for the speed, but that's the downside. If something bad happens like it did in Ohio, you see it very quickly in Maine, within a second. So you better be able to respond very, very quickly, faster than any human can respond. Because if you get a red alarm or red light and you got to hit a button, but that's too late, something's burned down, it doesn't take too much time to do that. So it's good and it's bad. Speed is a great answer, but it doesn't always work so well in slowing things down. What is the biggest problem with EVs today? Battery. That doesn't make any sense. I just said electricity can flow at the speed of light. Why can't I charge up my battery like that?
Chemical system.
Yeah, battery stores chemical energy, not electrical energy. Electricity is terrible for storage because it's like a road runner. Anybody knows what that is, right? Everything is speed, maybe Sonic the Hedgehog. What's a more current thing for something that's really fast? I said road runner, but that's nobody knows what that means. So Lightning McQueen, there you go. I'm not even sure what that is, but it's super fast, but to keep it in one spot, it doesn't like that so much. So storage, other than a capacitor, that's the only thing that can store electrons, if you will, is effective for that. But everything else you store mechanically, you store chemically. You can store some, well, I guess that would be mechanical or heat, basically thermal force, right? Because you can have potential energy or you can store chemical energy. So that's the biggest problem with batteries. It's not the electricity. I could fill up a battery in a nanosecond if the battery could accept that rate of charge. It just can't accept it. So it's the chemical problem. It's not the electricity. Although you start putting Tesla stations in every block, now the grid demand can get pretty high. That would cause a different set of problems. So one of the things EV manufacturers have talked about is, how about just having modular batteries? If you could go to a filling station and instead of like filling your tank, quote unquote, up with gas, why not do like a propane exchange? You know, when your propane tank for your gas grill is empty, you just change it out. Do the same thing with a car. Just swap out the battery, and then you can drive for 300-400 miles, get to your next filling station, do the same process over again. They've looked at that because the battery technology is getting better, but it's not getting better fast enough for widespread enough adoption, except for in Europe and China. China has done quite a bit. Yes, sir.
The cell phone now, for fast charging on the cell phone, you can charge your phone in 10 minutes.
Sure, you can charge a cell phone in 10 minutes, but how much capacity is stored in a cell phone? You're going to be able to take that for 50 miles down the road in your car? You're talking milliamp hours of storage. In these batteries, you're talking thousands of amp hours. So yeah, it's just not practical. I mean, if you look at a battery on a cell phone, it's probably not much bigger than my watch head. But in a car battery, like in a Tesla, it's the whole floor. Is the battery system, because you need to be able to get that much storage. Again, as we get better, we look at different materials. It may improve, but right now we're still a long way to go. So we talked about generation. That's where the power comes from. But again, it's not generating power. I hate the word generation. It's converting power from mechanical or chemical to electricity, right? Because I don't generate electricity. I convert some form of energy, mechanical or chemical into electricity. Then my load, it consumes power. And again, that pays the bill. And then the intermediate spot is the transmission system, because you don't want generation directly adjacent to your load, mainly because I don't want it in my backyard. I don't want to look at a nuclear power plant with that massive cooling tower, that's zooming over the horizon. I want that to be way off in the distance. So transmission connects anything. Why is this difficult? Well, power systems go up and down. Loads change. Transmission system, you can't run a transmission system at infinite demand. It will overheat, right? Just take a copper wire, and those aren't even copper, they're aluminum alloys typically, but that has I squared R, so I can't just continue to heat it up because eventually it's going to start to melt. It's called annealing when we talk about it from a chemical process, because you don't really melt the conductor, you just start to change the chemical properties so that it doesn't continue to work. You have path of least resistance. So you have no idea where your electricity is going to go. I can turn the output up on Main Independence Station, which is in VZ, and the power can go through Bangor. It can go up through Orrington and go a different route. It really just depends on how it's interconnected. So controlling power is very, very difficult. What about alternatives? Alternative energies are non-dispatchable in many cases. Is the wind blowing? Is the sun shining? If those two are not there, then you don't have that generation, which means you can't count on it. So those are called non-dispatchable technologies, and they are treated differently than dispatchable ones. Dispatchable ones would be hydroelectric, because you have a reservoir filled with water. It could be a fossil fuel fired power plant because you have a fuel source. Could be a nuclear plant, right? Because you have a uranium reactor full of uranium. And so those are dispatchable, which means you have a lot less unknowns. A couple things about power. So power is the instantaneous consumption of energy. It's a rate. That's why it's consumption. It is in watts, which is a joule per second, is not a joule. So 900 gigawatts is the generation capacity. That continues to increase each and every year. Mains is about 3.3 gigawatt and continues to go up, although not very quickly, because a lot of the generation, unless it's hydro or wind, nobody wants to build it. Our peak load is about 1.6, and our campus peak load is around 8 megawatts. Energy is that unit of joules, but hey, wait a minute. In my notes, I say kilowatt hours. That's not a joule. What did I do wrong? Well, it's the same thing, isn't it? Sort of. Kilowatt hour is 1,000 times a watt, which is a joule per second, times 3,600 seconds in an hour, right? Well, I'll just do 3,600 seconds. What am I left with? Joules. So on your bill from Versant is how many joules you've used. It says kilowatt hours because 1,000 times 3,600 is 3.6 mega joules. And if you use 100 of those, right, you can start to see that using a unit of joules to pay your bill is not really effective or productive. So we just do things in kilowatt hours. And some people actually pay in megawatt hours. If you're a big enough facility, like generating facilities oftentimes get paid in megawatts hours, not in kilowatt hours, because it would be too small. We consume about 3,600 billion kilowatt hours, and that continues to go up. Even though we talk about being more efficient, LED bulbs and more efficient appliances, we just want more crap that is run by electricity, right? How many people here have a car with power windows? Better question to ask, how many people have a car without power windows? You too? Okay. That's pretty unique today. Must be a really old car, or the mechanism is broken. 07? Wow, okay. No, pretty good. But you can just see people, I guess, are too lazy to use the manual crank on the windows. Yes, sir.
Does that last both points per year?
Per year, yep. So it's conveniences, right? How many people here have been to the gym at the university this week? How many people here ran on the treadmill? why won't you run outside? It's the same activity. And you're not using any kilowatt hours. I'm not making fun of you. I'm pointing out that that's convenience. You do it because it's convenient. I can run on the treadmill. I can get my sweat on 30 minutes. I'm done. Sufficient. Going outside. Oh, I got to stretch. And I got to go up and down hills. And I got to watch out for people. And so you're just getting more convenience with it.
Hot outside.
You should stretch.
You're college students. Nobody here stretches, right? Maybe like the elite track people or something like that. They stretch a little bit, but for the most part, you just start going. I'm almost 55 and I do a 5K every other day and I don't stretch. I jog probably a lot slower than you all do. So, but yeah, that's just what it is, right? It's convenience. All it is. Convenience, convenience, convenience. How many people here? It's a 2-story building, but if the fitness center was 4 stories, would you take the elevator to go up and down or would you take the stairs? Elevator? Which is interesting, right? Because you're going to the gym for what purpose? To exercise. Walking up and down the stairs, last time I checked, is considered exercise. But, and I'm not making fun of you, it's just it's a reality. People would prefer to take the elevator. Even if you're at the gym, when you're there to get exercise anyway.
I said the guy was like, you drive to the gym to run.
Yeah.
You could just run to the gym. That's
Run to the gym, right? Why drive to the gym when you could run? Again, it's just convenience, right? That's what we're doing it for, is convenience. Like been to an elevator, been to an airport, and how many of you use the walking sidewalks? The moving sidewalks. You can get from point A to point B a lot faster, right? You'll laugh, but I try my kids, it's like I try to make them walk. And they bitch and moan about it, but it helps them.
the new tech I saw, wage is like the belt you put on your legs. It helps you walk faster and remove less stress on your legs.
Well,
walking.
Yeah, if you're somebody who has, some sort of health conditions, that makes sense. But using your body the way it was intended is actually going to make it so that you don't need to use those things. Yeah. Like there is discussion with the military to use exoskeletons to help you carry more weight and not get fatigued. But that's because you're doing, 20, 30 miles wearing 50, 80 pound packs. There's a different need for something like that. But for most of us, we should be able to carry ourselves around for the 10,000 steps a day, whatever they recommend. So utility systems, anybody here from Holton or Kennebunk? They have municipalities. Madison, they have small munis where they have maybe 1,000 customers. That would be a small scale one. They're not as common in New England as they are down south. But you can get much bigger, like American Electric Power, which is one of the largest utilities in the world that has authority over multiple states to run the power. We talked about the 60 or 50 hertz, 400 hertz for airplanes because they want less weight and size. Do they even use frequency in airplanes anymore? Probably the old planes, but all the new stuff is all fly-by-wire, digital. They don't have nearly the same requirements that they used to. But all those old planes, those refuelers, using 70s technology. Yep. Yeah, and that's the old refuelers, right? They're not updating those. But if you look at the 6th generation stealth fighter, it's probably all fly-by-wire. No, it's all DC or computers, just super redundant. Ships and submarines, right? They're their own power systems. I've been on a submarine, and once it's off port, it's got its own 60 hertz system. They have 2 SSTGs, ship service turbine generators, that provide all the power for the submarine. Why do they have 2? In case one breaks. The only reason why they have 2. Each turbine can take care of the full demand of the ship, but if you're out underwater and you're 5,000 miles away from home, you don't want to rely on that single generator because stuff breaks. Bad thing, cars, 12 volts is really bad because look how big your wires need to be to run all that stuff. Anybody here updated their stereo with the super duper bass and whatever? Nobody? Well, the first thing you do is replace some of the cables, right? Because you got to pull a lot of current. But if you ran them at 48 volts, you could get by with much smaller wire. So we still are stuck on a 12 volt DC system. I have a plug-in hybrid. So I have a traction motor that goes to like 390 volts, but you can't run 390 volts off the car. So there are 2 batteries in my car, the traction battery and then the 12 volt battery to run the car accessories. kind of silly, but whatever needs to. And then any battery operated portable systems. Here are our interconnects. Make sure I'm not taking too much time. So we're in NPCC territory. You can see Western, you can see Eastern, and Texas. Texas is really interesting. If you remember from a couple of years ago, they had really crazy power prices in Texas. Nothing the federal government can do because that's all in its own territory. That's part of ERCOT. They're not even considered part of North America because they run DC lines between Texas and the continental US. So moving power is a little bit different going into Texas, but that's why ERCOT is specific to the one state because of the DC disconnect that you have there. Obviously, Alaska is a little different as well. And Hawaii, because there's not too convenient to connect. Nope, Florida is all interconnected. You can see, well, maybe it's different. Yeah, maybe it's FRCC. I'm not sure why. Well, it's still part of this interconnect here, but the regional operator is FRCC. But yeah, Florida is interconnected to the rest. So we're going to talk about transportation of energy because we said it's really good. It's really fast. It's Lightning McQueen, right? And 40% of all energy transported is via electricity. That's going to continue to go up, especially if EVs take off more and more. It was projecting much sooner, but because of all the things with policy changes in the current administration, that may not be as big. But if everybody, is worried about electricity and what it means, look at China. China is like 50% of their cars are sold are all EV. And 20 years ago, maybe even less, the Beijing Olympics, Summer Olympics with 2008, they were talking about seeding clouds because the pollution was so bad. They don't have to do that anymore because they've electrified their system. And so they figured out much cleaner ways to do it. They've got renewable energy projects that dwarf what we have in the US. They have the Three Gorges Dam, which is something like 50 gigawatts of new hydroelectric generation. And they're building another one here that's going to be twice the size of that. China also does nuclear. Nuclear's got good and bad things, for sure. A lot of bad. But what's good about nuclear? It's as efficient as any other power plant that's designed the same way. Generate, well, that's just a size thing. But you can make other generators that could be on all the time too. There's one big thing about that. Yes, sir. Burns clean, say more. What's that?
Longer.
Well, if you had a generator that was as well built, you can run a coal plant just as long.
Very little, not.
But the waste is really negative, right? That high level waste is a real drag. Low volume, yeah. Very close. What do you burn at a nuclear power plant? You're not burning anything. You don't put uranium on fire. You split the atom. So spent fuel is not burned. It just, it's less enriched uranium, essentially. So what ends up happening is you produce this much CO2. There's nothing is burning. You're splitting the atom. So per capita, believe it or not, nuclear is the lowest producer of CO2, even less than wind. Why is that? Because the power per capacity, like you're still going to build a plant, you need concrete, you need all this. So that is equivalent CO2. But a wind turbine, its density is much less. So you need a lot of wind turbines. And so if you were to compare per megawatt, nuclear plants produce less CO2 than any other technology. So it's clean. That's exactly right. But yes, it's the burning part that always confuse, because you're not burning anything. You're spending the fuel. Here's some energy pie material. So you can see natural gas is big, petroleum, kind of big. Coal is continuing to decrease. Nuclear is about 8% and holding pretty steady. And renewable is increasing slightly. Here is for New England for that same time period. You can see natural gas is number 1 and nuclear is number 2. And there are only 3 nuclear power plants in New England. There's 2 in Connecticut at Millstone, which is near Neantic, Connecticut. And the other one is in, I can't think of it. It's Seabrook. I was gonna say Salem, but that's New Jersey. Seabrook, which is just when you pass into New Hampshire, you see, I think the second or third exit is Seabrook. Those are the only 3 nuclear power plants left in Maine. At one point there, I think there were over 10, but they've been slowly dying off, if you will. And then number 3 is renewables. And we cheat a little bit in New England because we've had a lot of hydroelectric in New England for a long time just because of the topography. So it's not like we have to work really hard to meet any renewable portfolio standards because we're already there with hydroelectric. But Mass in particular is considered the California of the East, which anybody who's been to California or Massachusetts realize that that's not a valid statement, but they have tremendous amount of solar resources in Massachusetts, way more than what you would expect based on how little sun they get relative to California. And then a couple other things. Here's Maine. So you can see Maine, 80% renewables. A lot of hydro in Maine, right? And a decent amount of wind. Starting to see more and more solar, but solar is really bad in Maine just because it's not, we don't have great sun. Here's the energy demand over time. And you can see renewables are picking up and coal is decreasing. Natural gas is increasing. Here's renewable energy consumption. So again, I only include this one because if you look at this EIA, that's the Energy Information Administration. And for now, or agency, I should say, there's a lot of really good data in there. Again, I don't know what the current administration may change policies, but they do monthly reports giving a wealth of really good information. So I encourage you to look at their monthly reports if you want to get more information on that. Here's how wind has grown. And it's all tax incentives. That's one of the bad things about renewables is they really don't fly all that well until you give tax incentives. And I know, a lot of people get get upset. Why I can't talk today about renewables and a lot of the subsidies they get, but hydro and fossil fuel got a lot of those too. But remember, fossil fuels have been around for 100 years when they've been doing generated electricity. So they were given a lot of money back then to perfect different technologies. And so now they're as perfect as they can be. So it just takes more time for these and they'll get better. It's just that we have a lot longer a learning curve with fossil fuels than we do with renewables. Here's clean capacity by state. I'm always blown away. Look who's number 1. Big old state of Texas. Nobody in this class, I would imagine, would think Texas would be leading the clean power capacity. When you think of Texas, you think of oil, right? North and West Texas is wonderful, wonderful wind resources, amazing wind resources. So they're almost twice what California is because it makes economic sense in Texas. So big, big power there. So last couple slides here. I got a couple more minutes. I'm doing okay. So when we build power plants, because we want to make sure that we can meet the load, we have to figure out costs. So nuclear and solar have very high costs. Nuclear kind of makes sense. You better build these plants right or else. Why is solar so high? It takes a ton of land to build a solar facility. It takes at least 4 megawatts of land to produce 1 megawatt of generation output at peak sun conditions. So if you need 100 megawatts, you need 400 acres. That's a huge area. So the costs for the land are what kills solar. Also, the cells themselves can be fairly expensive. Those prices have come down a lot, especially as a lot of them are made in China, but still pretty high. Natural, yes, sir.
I hope you use like parking lot.
You can. Yeah, you can do that, but then you have to cover them. And in Maine, covering a parking lot is a good idea, except for the fact when it snows, now you get roof load with snow, and then you get a solar array that you always want to tilt at longitude, which is, let's say, 45 degrees, and now you have a sail for snow. So all that snow catches behind there and makes the load a lot more, and solar is not great. In Arizona, yeah, they have parking garages that, because it gets 120 degrees and you really need to put a car in a parking garage to make the car last, they'll put solar arrays on top of those, but that works in very limited spaces. It's not ideal. So that's why you see them on people's homes and they're always pitched at the roof line. It's not perfect. You'd rather be exactly at latitude, but yeah, you get that. So natural gas and oil, again, you can buy on the back of a semi, you can buy a natural gas fired gas turbine. But it's not going to be very efficient. And the operating costs are going to be sky high because you're buying fuel off the spot. And then coal, wind, and hydro tend to be in between. And then a capacity factor is how much a plant works or operates based on its full capacity. Here are some ballpark energy costs, which gives you the range and then the average. So you'll see this levelized cost of electricity in dollars per megawatt hour. This is over the life of the plant. That's what the levelized is. And so the lower, the better. Natural gas, a lot of volatility. So running off natural gas tends to be considered clean, but very, very expensive. Natural gas fuel prices can vary a lot, and you can see a lot of up-down action here. Solar, a little more stable. Prices have come down. And these are just on the arrays because you don't have to buy the fuel for solar, right? It's the sun. So there's no fuel cost of that. And I think this is my last slide. So now you're going to design a system that can handle this load variability. Up, down, up, down, up, down over the course of the day. And we saw the ISO Express. We even saw over the course of one day a swing from 10 megawatts to a peak of almost 16,000, 10,000 megawatts to almost 16,000 megawatts. So a 60% increase in over a 24-hour period. That's not easy to do. I wonder if the utility system does its stretching before it does that. What do you think? Not exactly. Okay. So that's all I had for today. For the next class, I encourage you to preview the slides. It's already been posted. And take a look at it, and we'll continue our introduction. Have a great day, everyone. Somebody's in the chat.
Yep. Paul, I had one comment, was the link that we had to click on was the last
Thanks,
link.
Casey.
Can you
Hopefully
hear me?
they'll find the right link this time.
Well, it's the one on Right Space is for the lab to get to here, not the
Oh, it is? Okay. I'll have to switch that around then. Thank you.
yeah, no problem.
All right. Take care. Bye. Yes, sir.
Hey, Paul, I just wanted to